Hi, everybody. My name's Galen Bascom. I'm with the AVS lab in CU Boulder, and I'm going to talk a little bit about the work that we're doing to model hinged solar panel deployments. So I'm going to start with why do we care about this? What's important? So previous work had looked at hinged rigid bodies attached through a central rigid spacecraft hub. But that was sort of in a particular case. So when the nominal angle is fixed, what happens, what sorts of oscillations are there when you have a hinged panel attached to the hub? So we wanted to extend that to cover more scenarios, look not just when that reference angle is fixed, but what's going to happen during deployments when that reference angle is going to be allowed to change over time. So this is an interesting problem because deployables are important, and having moving parts, hopefully as engineers, we know that can cause things to break. So I have here a picture of Lucy, sort of a topical example of deployments not going exactly as predicted. Of course, this solar panel structure is more complicated than anything I'm looking at here. We've got the fanning out motion that didn't quite go all the way in that case, but it highlights that there are a lot of interesting issues with these deployable structures. And some of the other work I'm doing is in fault detection. So I wanted to look not only at nominal cases of deployments, but also ways that we can model and show what happens in off-nominal cases, sort of like this. The nice thing about the way that we're trying to do this is that, as I'll get into in more detail, we're able to make relatively small changes to these mathematical derivations and small changes to the code base and get some complicated behaviors and some interesting results to come out. So looking at how to set this up, we're making a set of pretty strict assumptions. So first, the panel itself has to be rigid. So there's no flexing within the panel. In addition, I don't have it mentioned here, but we have a diagonal inertia tensor, an inertia matrix form of the tensor in the panel frame itself. So the way we set up and define this panel frame, we need it to be diagonal in that frame. The hub, we're also assuming to be of itself perfectly rigid. So the only non-rigid element of this multi-body system is this articulation about the hinge. That's all happening, we assume, along this one axis. And we model the hinge as essentially being a torsional spring. So it has a stiffness coefficient K, which is proportional to the displacement angle, and a damping coefficient that's proportional to that angular rate. So all the different reference frames that we set up, we have your standard vanilla inertial reference frame, that's N. We also have a body fixed frame, B. And then we have these three sort of panel frames. The hinge frame, which is fixed relative to the body and represents a particular panel angle. We have the S frame, which is the panel frame itself, and that represents where the panel actually is in space. And we have the R frame, which is going to be where the reference is. So in previous work, this R frame didn't exist. We were just, that entire theta was what the K and the C were applying to. But here we've introduced this new delta theta, which is just going to be the displacement relative to the reference. And that's going to sort of define the dynamics of how the hinge spring is going to operate. So all three of these last frames have the same sort of axis, and that's the rotation axis, this S2 hat, but R and S are displaced different amounts from H, which stays fixed relative to the hub. The S1 hat is anti-parallel to the center of mass of the solar panel, and all of these frames are sort of located about this hinge point H. And then, of course, the third unit vector is completing the right-hand set. with a, a positive rotation, like positive theta being defined by the right-hand rule. So those are our frames. And now we get into kind of the nitty-gritty of the math. I'm not going to go through every single step of these derivations. It's long and complicated, but feel free to look at the paper. And the previous works papers, all of that is laid out in a lot more detail. But the point is we're starting from first principle. So we're looking at F equals ma, we're looking at Euler's rotational equations, and from there we're taking steps to get these three sort of acceleration terms that we care about. We have the r double dot bn, we have the omega dot b relative to n, and we have the theta double dot. So b relative to n, that's going to be our body point b relative to the inertial origin. Omega bn is going to be the hub rate relative to the inertial, and the theta double dot is going to be how we're going to represent the panel. So we get the whole state of the system, the panel and the hub together with these kind of three accelerational terms driving the dynamics. So we have these two equations of motion, one for the translational and one for the rotational equation that we started with. The next equation of motion that we get is for the panel. So we only have to look at the torques and what's happening essentially around this S2 hat axis. So there we have the external torques show up, but we also have the damping and the stiffness coefficients that I was talking about earlier being applied to the delta theta and the delta theta dot. And again, we rely on Euler's rotational equations for the panel to get to a form of the panel equation where we can isolate the theta double dot. So that's kind of the key to this whole procedure is we have these set of interlinked equations, but in this equation, because we have the panel being connected through the rigid hub, we're able to isolate that theta double dot. So we have theta double dot in terms of the r double dot bn and the omega dot bn that we had equations for before. Just as a matter of convenience and housekeeping, we can rewrite the theta double dot equation to have these three terms, A theta transpose, B theta transpose, and C theta, to make it easier when we substitute it back in, because that's the third step. And sort of the key trick underlying all of this architecture is when you have one of these big multi-body systems, you get this big system mass matrix that's coupled in all these ways. But with these tricks, you can decouple the panel equation, like we just saw, from the other two equations and set the whole system of equations up in this form. So as you can see, the theta double dot term, what we're doing is we're just plugging it back into where you see the theta double dots in these two equations. And then we're just rearranging the terms so that we're isolating the r double dot bn and the omega dot bn in each of these equations. And whatever's on the right-hand side of these equations is what's going to show up over here, taking into account, the C theta, which we're rearranging the equations to have all these pieces. So the nice thing about doing it this way is you get this partitioned block matrix. So each of A, B, C, and D are 3x3 matrices. And there's a linear algebra technique called Schur's complement that lets you solve for omega dot bn and r double dot bn, doing just a handful of 3x3 matrix inversions. So you can see you're doing the A inverse computation and you're doing the computation of the inverse of this whole matrix. But everything else here is just addition, matrix multiplication, sort of fast operations. So that saves you from having to do not only this big 6x6 matrix inversion, but also, you know, if you hadn't decoupled the equations, the giant inversion of the 8x8 that you would have had then. So once you solve for the omega dot bn using this Schur's complement trick, and then similarly for the r double dot bn, you can use that to just, you know, solve the top part of this matrix equation. You take those and you substitute back into this same equation right here. You had calculated A theta, B theta, and C theta before, and you can just pop those back in. And that's where the back substitution of this whole method comes in. So those are your equations of motion, but then how do you implement them? And the way we do it is this software architecture that I've talked about a little bit called Basilisk. This is a big ongoing project to which I've contributed a small amount recently, but was started by other lab members in years past to implement this back substitution method so that it would be possible to have these kinds of fast, efficient spacecraft simulations. So it doesn't cover everything. You can't have an arbitrary spacecraft configuration, and Basilisk is definitely going to work for you. But what it does allow is when you can satisfy the assumption that all of your moving parts are kind of connected through this hub, the back substitution method is working, and Basilisk is a fast way, because of these linear algebra techniques that we've employed to implement these equations of motions. And because all of each panel is just a module that you add, you want one panel, you add a panel. You want another panel, you can just stick another panel on there, because the isolation of the two different theta double dots is sort of independent of each other, and you can just apply the back substitution method additional times. So this leads to a really modular structure for the software code, and you can plug and play with all of these modules. So in order to actually show some deployment scenarios in action, I was working on some new modules. So one thing is a panel motor to drive the deployment. I didn't do any detailed analysis of what type of control law I wanted here. I just popped in something simple, which is going to have a proportional and a derivative term. And if you look at the structure of the equations of motion, all this is really doing is kind of amping up your K and your C when you're doing your deployment. There's also a panel angle sensor, so to tell you what your panel state is if you don't have access to that information directly, and to add corruptions more crucially if you wanted to, so that your motor doesn't have perfect information. Last but not least, there is the profiler changing the reference. So that's kind of the key, is we have this new ability to change what the reference is. So the profiler is the module that does that and says, okay, now we're changing what the reference is that we feed into our panel module. Right now, we just have this simple linear profiler. You have a start time, you have a stop time, you have a starting angle that you wanted and a stopping angle. And it just kind of calculates a linear profile between those two angles during that start and stop time. Before the start time, of course, it's at the start angle. After the stop time, it's at the stopping angle. The nice thing about the derivation that we went through is none of it's dependent on that profile being linear. So we talked about maybe wanting to do some sort of smoother inverse tangent kind of profile, and all of that is possible just by changing this profiler module. Nothing else depends on the deployment being linear. So to set up a particular simulation, show what it all looks like, there's a spacecraft hub, there's a panel, and I've set it up with a solar power panel attached to the structural panel. So the sun in the simulation will kind of be a proxy for where the panel is. So I have it set up so that the panel is sort of lying flat against the hub's side in the beginning and then deploying out fully to a fully deployed angle. And then because I have the spacecraft pointing at the sun, as it deploys, you see a power increase essentially, just to show how these sorts of small changes in the code, just having the panel read in its state from the structural panel lets you show these complicated behaviors. In terms of particular values for K and C, I wasn't trying to be realistic. I just picked some numbers to show everything in action. And of course, I incorporated my motor and my profiler. I didn't end up using a sensor because I didn't add any noise, so I just fed in the panel state to the profiler. So for the nominal deployment, you can see sort of the behaviors that you would expect. Over here on the right, we have what the profile looks like. So you can see this is nice and smooth, nice and piecewise linear between the start time, which I have at 5 seconds, and the stop time at 85 seconds. But over here, when we're measuring the actual behavior of the panel, you can see these oscillations, and those are just a function of having this torsional spring as part of the simulation. We also wanted to look at how is the hub reacting while this panel is deploying. And as you can see, there's sort of that equal and opposite rotation of the hub as the panel deploys. Same thing with the rate of the hub. During this kind of steady period of deployment, you have kind of a steady rate here, but the oscillations are also reflected in the hub rate. And of course, in different amounts, just because of the differences in inertias, et cetera. The motor torque, you can see that it's changing over time during the deployment and as the angle settles. So that's kind of, because of the way we've set up the motor, that's kind of a proxy for that K delta theta plus C delta theta dot term. You can see that that's varying over time. Last but definitely not least, you can see the solar panel power. So even in the beginning, you can see that those pretty small oscillations in the panel are causing ripples in the power generation. And then there's kind of a smoother period here when the panel is deploying a little bit more smoothly. Of course, it's not linear for the power because you have this cosine of the angle relationship. And then it settles into kind of a steady state power generation at the end. So that's what the nominal case looks like. The off-nominal case, we just set it up to stop a bit short. So in that kind of anomalous case, it's only going half the distance in about half the time, and then we're saying it gets stuck. So once it gets stuck, it oscillates and settles around the lesser angle. So we're not at the angle we wanted. And because we're not at the angle we wanted, we also don't have the power generation we wanted. So just by feeding in those messages in the appropriate ways, we're getting these kind of complicated behaviors, in addition to having things like solar panel power, get the new panel state message. You could, for example, have your coarse sun sensors also be on the tip of the panel and have some of these effects sort of cascade down. We wanted to look at how the momentum and energy were affected. So more analysis definitely needs to be done here, but the simulation keeps track of the spacecraft momentum and energy states. So we were able to just take a look at how those are looking. For the momentum, I was expecting to not really see any momentum changes because a change to the panel should be matched by a change to the spacecraft with these kind of internal torques. So the rotational angular momentum is pretty noisy and small values. I'm not entirely sure what's going on with this orbital angular momentum. The values are minuscule, but it does look like it's approaching some particular value. So work to be done to figure out exactly what's causing that. The energy looks a lot more just how I would expect. We have sort of these noisy components in the orbital energy, but not really indicative of any physical changes in the orbital energy. But in contrast, I was definitely expecting some rotational energy changes because you're starting from spacecraft at rest, panel at rest, and they're starting to move. So of course that behavior is reflected in these oscillations. So as the deployment starts, you get a big change in energy, and then as the oscillation happens, that varies over time. This is kind of the smoother part of deployment when those oscillations are small. And then as the deployment stops, the rotational energy is going back down to zero, just like one would expect. So more work to be done. We definitely want to extend this to other situations besides just a single hinged rigid body. In the simulation architecture, we already extended to multiple hinges, but still having the body be rigid. So changing the reference on that multi-hinged rigid body should be like a relatively small extension of what we've done here. And then in the future, relaxing some of those assumptions, additional rotational degrees of freedom, and other more complicated types of deployments like you see in this beautiful artist rendition of Lucy. So that's what we're working on. Thank you for listening.